Okay, welcome back guys to another Random Coder episode. So today we're going to be teaching you how to perform a LCA search, commonly known as lowest common ancestor. So basically what it is given two nodes, in this case we'll pick 3 and 5, and a tree, which is right here. What is the lowest common ancestor, right? So an ancestor is basically any parent of 5. So basically from so if we define the depth of here, which is 0, 1, 2, and 3, basically it's the 1 to the k parent of your node are all ancestors of the node. Okay, so for example, in this example, 3 and 5, our answer would be 1 because 1 is the lowest one, right? It wouldn't be 0 because if it was 0, then it wouldn't be the lowest. And if it wasn't going to be the lowest, then you can just output 0 every single time and still get the right answer. And then one thing to note about trees is that it's going to have n nodes and n-1 edges. Okay, so normally the naive way to do this problem is to you could lift this to the same depth as 3 first, and then linearly traverse upwards. But lifting 5 to the depth of 3 is actually going to take O of n time, right? Because if you have a tree that looks something like this, a very unbalanced tree, then if this was your node, this was your node 1 and this was your node 2, then it will have to go all the way up here, and that's slow, especially if n is large. So maybe 10 to the 5th on that scale. So we want a faster algorithm than this. And more specifically, we want something that can be done in O of log n, right? Because this is actually going to be pretty efficient. So in order to do this, we have to learn how to do binary lifting, right? So there's the concept of binary lifting, which is needed in order to do LCA. So what binary lifting does is, if you want to BL, for example, node 5, and then we have a k, whatever, like an arbitrary number, then what it should return is the kth parent of 5. So for example, if k was equal to 1, then it would get 4. If k was equal to 2, then it'd be 1. If k was equal to 3, then it would be 0. Okay, so this should be done in O of log n as well. So in order to do this, there's a little math property of powers of 2's. So any power of 2 to the n-1 plus a power of 2 to the n-1 will be equal to the power the nth power of 2. Right? For example, 2 to the 3 plus 2 to the 3 is going to be equal to 2 to the 4. So 8 plus 8 is equal to 16. All right. And then you may notice that if we have this property, say we take 5 again, right? So first we'll have 2 to the 0th power, which is 2 to the 0th power, which is its direct parent, so the first parent, right? So we can take this first parent, that's a 4, okay? Now if we have 2 to the 1st power, that's its second parent. And if you recall, that's just node 5's first parent and the parent of that parent. Okay, which will be 1. And if you want powers of 2, which is the fourth parent, it's actually gonna go out, but it'll end up being 0. And then we'll have a case to we'll have some logic in our program to detect this, so we don't like to do something like -1 or -2. Though you could, but you can see how using this property. So using this property, you can build a table for every single one of your nodes. So for example, you got 0, 1, 2, 3, 4, 5. And then this will be the 0th power, first power, second power. We won't go beyond there because second power is already beyond. So 0's first power, this is just all gonna be 0. So first, the 1's ancestor, the direct ancestor of 1 is 0, and everything else is also 0. 2, also 0. 3 is 1. 4 is 1, and then 5 is 4. Okay, so I filled in these zeros because they weren't going to do anything anyways, but all we need is this first column for now. So we need this first column. Okay, so now let's start building. So if we want the second 2 to the first parent of 3, then what we need to do is we need to get 3's parent, 3's 2 to the 0th parent to be specific, and then get the 2 to the 0th parent of 3's 2 to the 0th parent. So that may sound confusing, but I'll do it. I'll do an example here. So 3's 2 to the 0th parent is 1, right? So you go here now. 1's 2 to the 0th parent is going to be 0, so this is 0. Okay, and then for 4, 0th parent is 1, so the same thing. For 5, 5's 0th parent is going to be 4, 4's 0th parent is going to be 1, so this is 1. Okay, and as you build it up, let's just call this 2D array up, right? So the formula for building this up is going to be up at node, sorry, up at up node to n minus 1 to that's n minus 1. So this is the formula, whoops, to keep in mind. It's very important. I'm going to put 3 stars over it. So once you have this up array, all you need to do is to figure out how to jump now, right? So you have the pre-processed information, okay? So we have 2 to the 0th power of 5, 2 to the first power of 5, 2 to the second power of node 5. Now, the question is, how are we going to utilize these powers of 2 to binary jump or lift up k nodes? Because you might have noticed already that 2 to the n sometimes cannot equal to k. For example, if k was equal to 3, you cannot find any integer n's, right, that will give you 2 to the n is equal to 3. That's not going to happen. Therefore, we will utilize a binary representation. So even though 2 to the power of n cannot guarantee it to be equal to k, but binary numbers can. So for example, we can use different powers of 2. So let's just say 3. 3 in binary is going to be 1 and 1, 0, right? So 1, 2, 4. This is the binary. And what you may realize is it's just 2 to the 0th times 1 plus 2 to the first times 1. And it's always going to be times 1 or times 0, right? Because it's binary, so the max is 1, right? So now, basically what we can do is we can treat this k as a binary. And every time we have a 1 bit, we will jump up this bit, right? So for example, if our k was 3, what we would do is first we would jump up 1 to here. And then we get to this bit, and then we jump up 2 to here. And you would notice that that's our answer. That's 3 up. 1, 2, 3, right? So you can use this binary representation, and every time you have a 1, you jump. It's basically just taking the binary and using it to figure out math. So instead of finding out the binary yourself, you can use bitwise operators. So when this number, I'll call it D because that's what I'll use later in the program. When this number gets shifted I times, and it is bitwise ANDed with a 1, and this is still true, that means there's a 1 bit, and we can jump. And then we can jump I times, right? Sorry, not I times, 2 to the I up. But we'll treat this, we won't actually say 2 to the I because our arrays are in powers of 2. So we'll just take our up, and then we'll put our node, and then we're going to lift it up I, right? So this is how we're going to binary lift. And after we binary lift, we just perform our usual. We just do what we usually do. We lift the lower node of the 2 up to the same depth as the higher node. After that, we lift these up simultaneously, and if we find an equal one, which this is, then that's our answer. Right? This node 1 is going to be our answer. And this is LCA done in O of log n time. All right, so now let's see how we can do this. So I'll head over to Visual Studio here. So we'll be doing this in C++. Okay, so first thing that we need to do is we need to declare our variables. So we need a depth array because we need to find out which one's going to be lower. So I'm just going to say given like a problem constant, the max, and I'll just state that's 2 times 10 to the power of 5 here. And then you can declare that here. And then we also need our up array, which is needed here. So max in. And then 20 is enough. 2 to the 20th is actually really large. So I usually just keep it at 20, but you never really need to go above it. If you do, then you do, but typically you do not need to go above 20. 2 to the 20 is a very large number. Okay, so what we're going to do now is we're going to construct our up. Now you may notice here that this tree seemed pretty easy how to construct it, but basically what we can do is we can use a DFS starting from the root node. We can DFS this subtree, right? And every time we can build it at that node. And the reason we can build this node, for example, if we already traverse 0, we can build 1 because everything that we've traversed in a depth first search, because every parent of this current node is going to be already traversed. Therefore, if it's already traversed, then we can build this row one at a time. Okay, so now let's go do that. So what we're going to have here is we're going to have a Dfs function. We'll call this vertex, or I'll call it N for node. So we can, once we enter the loop, we can already build the array. Start at I is at 1, 20. Okay, and we're starting at 1 because we're going to fill in the parent. The direct parent needs to be filled in before we can pre-process anything. So starting at 1, our up array at node at I is equal to our up array at up of the node bumped up I minus 1 power of 2 to the I minus 1. Right, so that was just a formula that we came up with a while ago. And then after that, we can traverse the adjacency list. So we actually need an adjacency list of edges here. I just say this is max in again. All right, so we have an adjacency list, and then we can go traverse our adjacency list. I did not define bi, so this is a vector of integers. So now what we're going to do is we're going to traverse the adjacency list of this node, right, which will contain all the edges, all the childs of this node. So we want to make sure that our x is not equal to our node because we don't want to traverse upwards. We only want to traverse downwards. Right, okay. And then we can set our depth x to be the depth at the parent of x, which is x up to the 2 to the 0th power. So we want to set that parent as our node real quick. And then we want to say +1. And this is because this depth is always going to be the depth of the parent, add 1 level down. And then what we can do is we can DFS down to our new node. And that's the end of our DFS function. It's not that hard. And then we can write our binary jump, right? So in our jump, we can have our node and then our k, which is our distance that we want to jump. So basically what we need to do here is we have to find the 1 bits, and then what we do is we jump when we find a 1 bit. So I'm just going to loop from I to 20, which is very big. So what's going to happen is if this number, if k, this in parentheses, if k shifted right, if k shifted right I times and bitwise and of 1, if that's still 1, then that means we have a 1 bit. So what we can do is when we have a 1 bit, we want our our node to be equal to its jump. So we want to jump up 2 to the I time, 2 to the I powered number of times. So this is supposed to be node, right? So once we jump up this many times, at the end, we can just return the new node, and that'll be our answer. So for our LCA part, it's going to be, we're going to call it LCA, and we're going to take in 2 nodes. So node A and node B. So first, if A is less than B, sorry, depth A is less than depth B, for consistency's sake, we want to swap A and B because we are always going to assume that A is the lowest lowest node. So we want to jump A up to the depth. We want to jump A up to the depth of B, which means it will jump up A minus B, right? The depth of A minus the depth of B times, which will get it up to the depth of B. Because if you think about it, a little comment here. So let's imagine, so depth of A plus depth of A minus depth of B. You'll realize that it's depth of 2A, but really it's a minus action here, so it's going to be minus depth of A plus depth of B, which is going to be equal to the depth of B. And this is minus because the depth is from, I'll do a comment here, it's from 0, 1, 2, 3, 4, 5. So you want to minus subtract that instead of adding it, which will give you depth of B. So once we jump, if A is already equal to B, then we can just return A or B, same thing. Otherwise, we can reverse traverse from I equals 20 to I equals 0. And then every reverse traversal, we just lift it up to the I power of times. So 4 I is equal to 20. I is larger than or equal to 0. I minus minus. What we want to do here is we can use our 2 pointers approach. So we're having temp A. Temp A is going to be equal to up A I number of times. We have temp B is going to be equal to up B I number of times. Okay. And if temp A is equal to temp B, or not equal to temp B, then we want to keep jumping, right? So we're basically starting from the biggest jumps and going down to the smallest jump. And that'll guarantee us the lowest ancestor. So basically, if it's not equal to each other, then we can keep lifting it up, right? So A is now going to be equal to temp A, B is now going to be equal to temp B. And at the end of this, we want to return the parent of one of them, because we said when they're not equal, we lift them up. Therefore, when these two are equal, we actually never set A to temp A and B to temp B, so we want to have the direct parent of them. And after that, your LCA is basically complete for the time being, and then you can now treat your problem how it wants you. So I'm just going to do a quick input to test this. So I'm going to read in N, which is the number of nodes, and I'll also reading E, which is going to be the number of edges. Define E up here. So we're reading N and then E. Now we're also reading Q, which is number of queries that we want to query. For simplicity's sake, I'm just going to put, it's just going to be 1, because we just want to test it. But anyways, so in this, we're going to have a tree. So it's going to go into 4i until n minus 1. And then every time we're going to read in integer b, and then we're going to read in integer b, and then at integer b, we will push I. So basically how this input is going to be structured is that I'm going to give in an array. So for example, if n is equal to 2, what I'm going to do is I'm going to give an array of numbers from greater than or equal to 0 and less than n. And what this means is the so at index 0 or just 1, so this 1 is going to be the parent of the index. So here's the index, and here's the parent. Right? So 1 is going to be a parent of 0, 0 is going to be a parent of 1. So the resulting tree doesn't actually form a tree because you're only supposed to have one edge and not two. So that'll be how it is. So now that we have pushed our numbers in, what we could do is we could now set our zero's parent is going to be equal to 0, and our depth at 0 is going to be equal to 0 as well. After that, we can DFS from our root node, which is going to be 0, and we should be good to go. So now all we need to do is for I until our query is reached, taking the two integers a and b. And then what we do is we can print out the output to see out LCA between a and b, and a new line. Get rid of this at the end, and that's basically how you write an LCA program. So now we can go test it. Okay, so I'm gonna erase this part. Okay, so how this input is gonna work is we're going to have n, which is going to be 6. And then after those lines, what's going to happen is we're going to say, starting from here, we're going to have the parent. This is the parent. Sorry. 0 is going to be the parent of 0. 0 is going to be the parent of 1. 0 is going to be the parent of 2. And then 1 is the parent of 3. 1 is the parent of 4. 4 is the parent of 5. So this is a test case that we will expect. But this 0 is actually going to be truncated because the parent of 0 is always going to be 0. So in here, we'll make a slight adjustment. This is actually going to be +1. And the reason is because here's going to be, this is 0 is the parent of 1, 2, 3, 4, and 5. Right, so it's going to be +1. And then our query is going to look like this. So our query, let's just say we're going to have one query this time. So our query, let's just say it's 1. It's going to have two numbers, node 3 and node 5, and it should output 1 at the end. And then one slight adjustment to make here is that we actually don't need an edge because a tree has n-1 edges. So let's just run this real quick. 6100114, 6100114, and then our query is 3. Yeah, 3 and 5. So we got 0, which isn't quite right, and let's see what's going on in here. 3 and 5. What we can do real quick is we can print out our up array. So from I to 6, yeah, and then from j to 3 is enough. We can do is here, we'll print out the I, And then here we'll print out up at I J space. Here I'll print out an empty line. And let's see what it gives us. Okay, so we got 000 11410, which seems like the array was set correctly, which is good. So our array here was set up correctly, and we want to find the common ancestor of 3 and 5. So it gives us 0, which means our jumping or LCA could have had a mistake somewhere. So what I'm thinking about that we should do is we should print out our jumps as well. So what we can do here is let's just make sure that our code is correct. So you jump up. Okay, this seems correct to me. Yep. Okay, so let's check our jump here real quick. So you want to make node n up I times, which is also correct. Okay, so